In previous videos on uncertainty analysis, I've told you that in order to calculate bias, you need to write the derived quantity in terms of direct measurands. But there are some situations where that's not possible. In that case, we need to understand the concept of correlated and uncorrelated quantities. We'll just rewrite the rules to say that we need to write the derived quantity in terms of independent quantities instead of direct measurands. Independent quantity is a more generic term, and direct measurands are the most common and easily identified type of independent quantity. But we need to be a lot more careful about calling anything else independent. Independent specifically means that the determination of any variable in this equation must be independent from any other variable in the same equation. The reason for this is that when we take the root sum square of our weighted biases, we are assuming that their variation is random and uncorrelated. That is, each variable can be perturbed up or down without any effect on the others. But if two or more variables always move in a known direction relative to each other, that is, if they are dependent on one another, they are considered to be correlated variables. Let's take a look at an example. For this example, I'm going to use a single wavelength laser absorption spectroscopy via Beer's law. That's a mouthful of vocabulary that we're not going to discuss here. If you really want to understand Beer's law in depth, I've got plenty of other content available for you. Here, what you need to know is that if I shine a laser with a specific wavelength and known intensity through a sample that contains some unknown concentration of a chemical that absorbs that wavelength of light, then a lower transmitted intensity of the beam will emerge from the other side. If I know the temperature, pressure, and path length of the beam through the sample, and absorbance characteristics of the chemical, that is, the absorption cross section, along with those initial and final intensities, then I can determine the molar concentration of the chemical I'm trying to measure. Of course, everything I do is in a combustion shock tube. This is a cross section of my combustion shock tube test section where I'll measure the concentration of combustion chemicals. So my laser beam passes through here. My path length is the inner diameter of the tube. I measure initial intensity by vacuuming down the tube so that my beam passes through 0 molecules and then into the signal detector here. Since the beam is passing through a vacuum, the beam that enters my signal detector is essentially the initial intensity of the laser, corrected for any effects of the optics in its path, which are constant. So I could call this signal my I naught, but I have a couple of corrections I'd like to apply to the signal to reduce the bias error. First, we need to realize that the laser output may be slightly variable, which will cause variation in the signal intensity that is not associated with the sample. I'd like to correct for this variation in laser output. I do that by placing a reference detector here, which outputs a reference intensity. This reference only changes in response to the laser intensity, which should be common across both detectors. So if I divide my signal intensity by my reference intensity, I now have an I naught that is insensitive to laser output variations. But wait, there's more. If I block this beam momentarily, I'm recording in what I call dark mode. Both detectors should sense 0 laser intensity. But if I look at the outputs of both detectors, I might find that their output voltages are offset slightly from 0. This offset is a directional bias. Luckily, we can correct for this bias simply by recording these voltages in dark mode and subtracting them from the voltages with a full laser signal. We call this dark mode rejection. So now we can talk about correlated measurements. Technically, I have 4 measurements here. I took 2 measurements at a time with 2 separate detectors. But 3 of these measurements were only taken to compensate for known errors in this measurement that I'm actually interested in. They're all correlated to that original measurement. These 2 measurements are correlated because they're measured by the same instrument in very close time proximity to each other. This is just the instrument bias inherent to this. Same argument here. The numerator and denominator are correlated by the laser power. So technically, I naught is a derived quantity, not a direct measurand, but it is an independent variable. So instead of treating it as 4 direct measurements, I'll just treat it as a single independent quantity with a bias equal to the noise. There are plenty of ways to quantify detector noise. I'll use a 95% two-sided confidence interval determined from a student's t-distribution, taken over thousands of data points for a single acquisition. We can apply the same set of arguments once we put a sample in the tube. I'll block the beam again to get my dark offsets. The transmitted intensity is the signal detector's offset corrected intensity reading with the common laser noise mode rejected by dividing out the reference detector's offset corrected intensity. These are all correlated in the same way as the initial intensity was, so the bias in the transmitted intensity is quantified by the noise in the derived but independent quantity I sub t. Now, if we go back to Beer's law, I figured out how to get the bias in the laser intensity readings. R is the universal gas constant and has negligible uncertainty. The path length is the diameter of the tube, which was measured after manufacturing, and its bias is just the uncertainty in the micrometer used to measure it. But now we see that the absorbance cross-section depends on pressure and temperature, so that means it's correlated to those. And we need to determine the bias in our pressure and temperature readings, which, as I explained in an earlier video, is quite complicated. Here I've depicted the sample in state 1, which is before the shock wave moves through the sample. In this state, I can directly measure the temperature and pressure and deal with the correlation in the absorbance cross-section. That's fairly easy. But I'm also interested in tracking composition in state 5, which is produced by inducing a shock wave that travels down the tube, leaving shock-heated gas behind it referred as state 2, then reflecting off the end wall and shock heating the gas near the end wall one more time, leaving the sample gas in state 5, which is typically on the order of 1 or 2,000 degrees Kelvin. Let's assume for this entire slideshow that we're solving for a steady state 5, so we won't worry about rising or changing P5 or T5. In this state 5, I might be able to measure the pressure directly, but there are some complicating factors that I can't get into in this video. I can't directly measure T5. So here, let's also assume I need to calculate both of these, T5 and P5, using other direct measurands. I made a whole other video walking through that procedure. The end result was that both of these quantities could be calculated primarily as a function of the state 1 conditions, the incident shock Mach number, and the specific heat ratio. So both of these are derived quantities, not direct measurands. The standard method for dealing with that would be to rewrite these two derived quantities in terms of direct measurands and then plug those equations into Beer's law. There's a problem with that. Both of these require an iterative solution. That iterative solution was the subject of another wildly exciting video of mine, and its conclusion is simply that T5 and P5 cannot be written in terms of direct measurands. So then, how do we calculate the bias? Well, if the incident shock Mach number or the specific heat ratio are perturbed, those perturbations will cause T5 to go in a specific direction, and P5 will always change in a related direction because it's dependent on them too. So T5 and P5 are correlated. Absorbance cross-section is a function of those two, so it's correlated as well. So we need to replace these with uncorrelated or independent variables. This one is actually pretty easy. These quantities are not independent of each other, but if I rearrange Beer's law a little bit, this quantity in red is independent of everything else. So I can treat this as a single independent quantity, and I can determine the bias on that quantity by performing a sensitivity analysis using perturbations in the direct measurands used to calculate T5, P5, and sigma. The process for that sensitivity analysis was covered in a separate video. So now the bias in the measured concentration of our sample at state 5 is the root sum square of the weighted biases of transmitted intensity, initial intensity, path length, which is again the tube diameter, and whatever you call this. Usually I work an example for these problems, but I'm already starting to put you to sleep and I've done examples of all the required math in other videos. So I hope that just the logic of the process is enough for you this time. And I hope this was helpful.